Hello, everyone. I'm really glad to be here. I would like, first of all, to thank organizers for the great event, to all of you who also made it possible to happen. And I also want to ask several referees who were referring papers on dark matter, which my collaborators and me published during last time. And the reason for that is the following. Whenever a report was coming, it was a question, how can you have that much of dark matter? We never went to something really exotic, really extreme, in my opinion. 1% or so, but the question is absolutely reasonable. How is it possible to have that much of that? And I will try to answer that question with a mechanism which is related to interaction of dark matter with itself. Yeah. So as an introduction, probably I want to mention what is known to everyone. The most of our universe is dark, which means that we have quite a lot of that substance. And if so, then it's natural to expect that it also can appear somewhere else, for example, in neutron stars or other compact objects. And you already heard quite many times during this meeting that presence of a sizable amount of dark matter inside of compact objects can sizably modify the properties of those objects. The first what could come to your mind corresponds to mass radius diagram. Thanks to Afonso Avila, I have this beautiful plot which was shown on his poster. And here you can see modification of the mass radius diagram of a neutron star calculated with purely hadronic matter when some amount of dark matter is added there. Here you also can see what happens to cooling curves of this object, and physics is quite simple. You add dark matter, you create core, it feeds gravity that compresses matter, which allows you to have higher densities, which opens some channels of some processes which are responsible for cooling. All in all, the result can be significant, but for that you need to have quite a lot of dark matter. I hope you can see from this figure that fraction is, as I said, order of percent, and it's really a lot. The question is how to accumulate that much. And what could come to our mind as probably the most conservative picture, which doesn't assume presence of dark matter in a protostellar matter cloud or anything like that, corresponds to accretion. And here I would like to cite this paper, which gives this simple parametric expression for the accretion rate. So if you know several characteristic quantities like density of dark matter around the object which accretes, and if you know mass of the dark matter particle, then you can calculate this quantity. And here you can see a simple application of this expression, and it gives such a value of the accreted dark matter amount within a period of 1 gigayear, which is already not that different from the age of the universe. And we see that the quantity is quite small. It's way smaller than what was shown on the previous slide, right? And from this, I'm coming to another question. If we account for self-interaction of dark matter, which wasn't present here, can we have any modification or not? Short answer is yes, but let's see how it works. Before that, I would like to briefly mention this scenario, which is going to be presented. So first of all, I'm not considering anything which is light, because in addition to accretion of dark matter, it also can evaporate from the compact object. And that's another complication, and I'm not going to talk about that now. And in order to omit that, I simply consider not too light dark matter particles, more specifically 1 GeV of mass. It's also not mentioned here, but what is important is that dark matter is not self-annihilating. It simply means that it's not symmetric with respect to particle-antiparticle conjugation. That provides it with possibility to stay inside the star and modify its properties. Finally, I also want to mention that we start with zero amount of dark matter, as was said before. I guess it's the most conservative picture you can imagine. Also, there are several simplifications, like ignoring multiple scatterings, which means that if you have at least one act of interaction of your dark matter particle with a stellar medium, then you count it as the one which was accreted. And yes, that's it. Now let's take a look what's happening in that case. But before that, I would like to give you some intuition, and that corresponds to considering a toy model. It is formulated by this simple expression which relates derivative of temporal derivative of the number of dark matter particles inside of the compact object to the accretion rate, which is parameterized by this simple formula. It has just three important ingredients. The first one is flux, which just shows how many dark matter particles penetrate the star within the unit of time, within the unit of area. We also have to somehow quantify probability of the particle of dark matter to interact with the stellar medium. And that's quantified by cross-sections, which sit here. One of them corresponds to interaction of dark matter with baryon matter, another one with to interaction of dark matter with itself. And finally, we have these quantities which are nothing else as amounts of scattering center, so amount of dark matter and baryon matter inside of the star. What is a good fact about this model? It's extremely simple to be analyzed. You can easily integrate it. And it's what you're obtaining under the condition of zero amount of dark matter at the initial moment. In the absence of dark matter interaction, so when this term is gone, you end up with just a linear dependence of accreted dark matter, which seems to be quite simple, right? The more you wait, the more you obtain. At the same time, when you account for this self-interaction of dark matter with itself, it becomes completely different, right? And what is most interesting about it is this exponential scaling. So just because of having this term, you obtain completely different functional dependence of this quantity, and that possibly can make some difference to amount of dark matter which can be accumulated in the neutron stars. So I hope with that you already might think where we're going, and now I need to make it a bit more specific. So I need to quantify several aspects of the model. So first of all, that corresponds to dark matter cross-section, because as we saw in the previous slide, it appears in the formulation of the model. So first of all, I want to briefly remind that interaction of dark matter with baryon matter is extremely weak. So here we have a collection of results of different studies, and more or less, in order to be safe, we can take something which is here, and then we can convert this value given in square centimeters to something which is more familiar to me, so squared Fermis. And we also took really conservative estimate, because if you take something which sits here, you would have something like 10 to minus 20 Fermi squared. But in order to be really conservative, 10 more orders of magnitude were thrown away, and this is a value of the baryon matter dark matter cross-section which is used further. With self-interaction situation is not that clear, because obviously no experiment so far gave us any piece of information on that. On the other hand, numerical simulations of the well-known Bartlett cluster gave some constraint on the ratio of dark matter self-interaction cross-section and its mass. And if being converted to these units, we have something like 0.2 Fermi squared over MeV. And that's a maximum value, which can be probably called not really crazy, more or less realistic. Another element of the modeling corresponds to inner structure of the star, which accretes dark matter. And in order to know that, you need to solve a system of two-coupled TOV equation, two because you have two components, baryon and dark one. And in order to make it a closed system of equations, equation of state should be fed there. And we used baryon 1, which is given by the DD2 equation of state. I'm not going to tell much about that because Mahbub Shabra gave an extended talk which was related to many aspects of this modeling. I only want to mention that black curve representing mass radius diagram obtained with that equation of state seems to be quite okay. It respects many observational constraints, and therefore it's okay to use it. Finally, for dark matter, we use probably the simplest possible model. Just a model of non-interacting spin 1/2 fermions. Why fermions? Because we didn't want to have another parameter, like self-interaction coupling of dark matter. And because of that, in order to gain some pressure, it was necessary to have fermions, not baryons. That's the reason. This is formalization of the equation of state given in the grand canonical ensemble. Again, a bit technical aspect, but what is important is that the only parameter related to this equation of state is mass of the dark matter particles. And finally, in order to make modeling, we also need to know how much dark matter comes from outside. And in order to know that, we need to know its distribution. Assuming equilibrium of dark matter with itself, Boltzmannian energy distribution was prescribed. It can be given such a form, and it has two parameters. In order to give them some meaning, we have to remind ourselves that energy momentum of this distribution is nothing else as number density of particles, and mean energy can be calculated in such a way. So therefore, these two parameters, C and beta, can be obtained as functions of those two quantities with a direct physical meaning. In order to quantify somehow this parameterization of the distribution and use it later in the calculation, an Astor profile was used. And here you can see what's parameterization of that. In fact, that quantity simply gives you mass density of dark matter as a function of radial coordinate within our galaxy. And this value of this mass density somewhere close to our planet was used in order to fix the rest of the parameters. So here you can see plot showing several distributions of dark matter, and all of them sit here. What is important, quite many orders of magnitude covered here. Therefore, we have something to play with. Now we can finally start to calculate dark matter accretion rate. More details on the derivation can be found here, but probably what I want to mention is the following. It's really convenient to parameterize phase space of dark matter with energy and angular momentum relatively star. And it turns out that only angular momenta with a value below a certain one can be accreted, because otherwise simply you don't have any crossing of the trajectory of dark matter within the stellar medium. If you perform some mathematical operations, which are quite straightforward, and if you account the probability to interact with any scattering center is given as an integral over the path of particle, it's possible to end up with such an expression for the accretion rate. What is really important here? Depending on amount of dark matter, distribution of densities of dark matter and baryon matter inside of the star will evolve. Therefore, at each temporal moment, it's important to solve a system of two coupled TOV equations. Once that solution is obtained, it's possible to perform this calculation of the accretion rate, and it's possible to feed it. Excuse me. Yeah, and it's possible to feed it to this equation which defines time dynamics. But before that, let's take a look to the accretion rate, how it depends on amount of dark matter inside of the star. So this red curve, it gives what we have in the absence of interaction of dark matter and baryon matter. And in principle, it looks like constant. It's not, it's slightly dependent on this quantity just because of reorganization of distribution of baryon matter. But up to really high degree of accuracy, we can say that it's constant. However, when interaction of dark matter with itself is present, situation is completely different. You can see it here. And modification of this accretion rate is quite significant. Therefore, we can expect that something interesting also might happen for the amount of accumulated dark matter. And that becomes clear just because we notice some similarity with the toy model which I was showing before. So accretion rate depends on amount of dark matter in both of these cases. Therefore, probably we can have some similarities in the dynamics in the toy model and in something which is a bit more realistic. And here you can see amount of dark matter accreted shown as function of time given in giga-years, so period compatible to the age of the universe. And indeed, when having a stronger and stronger self-interaction, we can accrete more and more dark matter. At some point, we approach to a regime where this quantity is of order of %. So it's already not that far from what was reported by several speakers during this meeting. And these are my conclusions. They're really short. So self-interaction of dark matter seems to be really important aspect of its accretion. And it's also possible to, depending on the values of the rest of the parameters, it's possible to accumulate sizable amount of this substance in the compact objects, which later will strongly modify their properties. Thank you for your attention.
Questions?
Thanks very much for a very interesting talk. So typically, people, I think, would say that there's a limit to how much dark matter you could accrete onto the neutron star just based on how much dark matter gravitationally infalls into the neutron star. And that's because you can think about a gravitational accretion radius where the dark matter has no self-interactions, which will give you a factor relative to the neutron star size of about 1,000. And then you can even think about Bondi accretion, which should be like the limit of purely efficient self-interacting material accretion onto the star. And that'll give you an enhancement to your effective collection radius relative to the neutron star size of about 1 million. But even if you had perfectly efficient Bondi accretion, if you just put in a halo dark matter density and let it run for 10 billion years, you would get up to like less than 1/1,000,000th the solar mass of of material accreted. So I'm wondering if there's something special about this where the dark matter is like very fluffy or extends physically much wider than the neutron star itself, or what might be going on.
Thank you. It's really interesting. In this particular case, that possibility was excluded. But in fact, if we consider scenario mentioned by you, so halo, yeah, extended distribution of dark matter, then accretion rate is going to be even larger, just because of geometrical reasons. So that's it. But here, as a first step, it wasn't considered. And actually, I guess it wouldn't be really okay to consider something with really extended configurations of dark matter, because in that case, also evaporation would have to be considered. But I didn't want to make that complication, so okay. So far that possibility is omitted.
How is your model accreting 1% of the neutron star's mass in dark matter? Is that for a local dark matter density that's very, very high?
Yeah, yeah.
Oh, okay. I see.
you probably can see the value. Oh. Yeah, which is given here, 10 to 15.
Oh, I see. So
it's still how to say? It's still not the most extreme of what is shown here. Yeah.
Oh, I see. So like in a very spiked density near
right,
the black
so
hole.
It doesn't correspond to something next to our world.
Okay, got it. Thank you very much.
Another question? All right, so let's thank our speaker again.